Hi, everybody. Thank you for joining us to the first public talk on Apache Liminal, an incubator project. I'm Lior, and Aviem will join me at this talk. Please feel free to ask your questions in the chat area during and after the talk. So, first few words about us. I'm Lior Schechter, the CTO at Natural Intelligence. I started my professional career 20 years ago doing product and cyber. After completing my engineering studying, I deep dived into the area of domain-specific languages, building a generic DSL engine and writing many articles on the subject. In 2009, while joining an edtech company, I got first introduced to the Hadoop ecosystem in its early days. So we needed to process billions of daily events. We built this very cool ETL engine, compiled Hadoop O18, and installed it on gamers' workstations. And the magic happened. In 2015, I started to work on ML, incorporating machine learning features into my products. So in the last 5 years, I've seen how the ML AI paradigm evolved and matured to become a standard de facto. Half a year ago, we decided to share Liminal as the Apache Incubator project. Aviem, your turn.
Thank you, Lior. Hi, I'm Aviem. I'll be joining this talk as well. I'm data tech lead at Natural Intelligence, and my specialties are data platforms as well as open source software. And in my free time, I like to play the card game Magic the Gathering. And back to you, Lior.
Great. So we will start with describing the motivation which drove us to develop and share the Liminal project. There has been a tremendous evolution in recent years in our ability to build and run machine learning models. Hundreds of solution companies have formed and are working on maturing existing technology and building new initiatives. I believe that the vision of data scientists working end-to-end from research to production is very close to reality. Nevertheless, the ecosystem is still shaping, and a lot of focus and many resources in academia and industry are working on the next evolution of machine learning, which will increase its agility and robustness and make it accessible even to smaller organizations. Current focus is on AutoML, monitoring, and MLOps. So this is the state of the ecosystem. Let's jump to speak about natural intelligence and see how the stories relate. Natural intelligence, we are a global leader in multi-vertical online comparison marketplaces. Our great technology matches between consumers and brands, assisting consumers to make more confident and faster decisions while helping brands to grow. We are a bootstrap company founded in 2009, and we work in a variety of verticals like mortgage, insurance, meal delivery, home warranty, and many, many more. We have started our journey to productize core business functionality using machine learning and AI about a year and a half ago. The goal was to take few areas at the core of our operation and automate them using machine learning. One focus area is the website personalization and ranking. This is, of course, our bread and butter. And the second one is around AdWords bidding. So we are among the 50 largest AdWords account worldwide, and we decided to build our own machine learning-based bidder. So how did we approach this challenge? I believe we did same as most companies. We had a very good data platform. It proven to be effective, robust, and scalable. So it made perfect sense to add to it the machine learning ingredients, mainly the Python libraries like scikit-learn and NumPy, and many more, of course, and the Flask server for online inference. Again, I believe many organizations go through this route as you have a proven and a stack that you rely on, and so evolving it to address more use cases is the way to go. The problem we encountered, and I must say, even few weeks after we started, is that data scientists are struggling in making things work. It happens both in local environment and in staging and in production. Practically, they can't really focus in algorithms. We call this the orchestration barrier, and it stems from the diversity in infra, GCP, AWS, Azure, and many more, the amazingly high number of languages, platforms, and libraries that are needed to build such workflows. So the orchestration barrier, of course, is something that impacts our ability to deliver machine learning features and solution in quality. And I believe that the impact of it is that the time to market of such features is often too long and most of the time unpredictable. So this is where we paused and, of course, looked around to find an existing solution. So we reviewed both open source and commercial platforms or solutions, but could not find anything that fits our architecture and vision. I won't deep dive into the details of the comparison as the time does not permit it. I intend to write a blog post on the subject in the near future. Anyhow, I hope that through the characteristics of Liminal and the demo that Aviam will show, it would be apparent why there isn't such a solution available. So let's see what's Liminal is about. Our one-liner is very simple. Is let data scientists focus in data science from research to production. How do we do that? So first and foremost, we have our domain-specific language to express orchestration and provisioning concerns. It abstracts away the complexity of the underlying technology, providing high-level abstraction for configuration and tuning. In many ways, Liminal enables data scientists to define their machine learning system using configuration from feature engineering to production monitoring, and the framework takes care of the infra behind the scenes. The DSL itself is, of course, extensible in Python through our plugin architecture. It is minimalistic by nature. As I said, it is a wrapper DSL, which generates the runtime artifacts for the technologies that do the actual work. So it can be adapted to any stack that exists in the organization. All you need to do is plug it into Liminal and get the orchestration capabilities. The solution is, of course, scalable as the technologies you have chosen beneath it. So if you chose wisely, Liminal won't add to the complexity or limit the scalability. And lastly, it is open source, since both myself and Aviam are a big advocate of the open source community. We've been working with it for many, many years, and it made perfect sense for us that if we develop something that is not at the core intellectual property of our company, and yes, natural intelligence, what we do is comparison websites, not a machine learning platform, it would be perfectly logical to contribute it to the community. I must add, as a CTO, that I see a great value of more companies joining the effort and making the platform mature faster. So I really call both individuals and companies to join us to this very cool effort and made machine learning accessible even more and make data scientists even more independent in their daily work. So now we will deep dive into the details of the Liminal way Aviem, it's all yours.
Thank you, Lior. And now what I would like to do is take you on a deep dive into how Liminal works. So first, let's discuss the problem that we're trying to solve. As you can see by this immense graph, the problem of getting code from data scientists to be deployed as production-grade applications in production, including training on a schedule, batch and online inference via a serving layer, and integrating with all of the underlying platforms and infrastructures is a massive feat to put on a data scientist to do. And we want to take this problem away from them and give them the easiest way from science code to production applications. And with minimal effort within the organization for any engineers or ops, as we can manage to make this pluggable into their existing architecture. So that's a big problem to solve. It's very complex. How do we intend to deliver on that? So at the center of any software development, there is the software development lifecycle, which repeats. And usually we start with some application developer, in our case, a data scientist who works on their IDE, in our case, coding some algorithms. From there, they usually push their code to some source control. And usually from there, we get some sort of CI/CD pipeline, which will compile that code and deploy it to runtime. And the runtimes can be varying as well. And from the runtime where our applications are actually running, we send out logs and metrics so we can create monitoring and alerting on those to deliver feedback to the application developer, and that closes the cycle in which they develop, deploy, and get feedback so they can improve the application. So again, this is a lot of things that we don't want a data scientist to have to know to do themselves. We want to abstract these away. So how do we want the data scientist to interact with the platform in order to achieve the software development lifecycle that we desire? So all that we ask of a developer of a Liminal app is to add one file to the repository named Liminal YAML, which defines the application in Liminal's configuration language, which we will now see. And this will abstract away all the problems that we referenced before. And the only thing they have to get over is configuring their application in a very simple manner, which we will now deep dive into. So how does this YAML file look like? You have a name for your applications and an owner. Then we have a section of what we call services. And services are applications that are constantly running and receiving some requests from the outside for some value, and they serve that back to whoever requested that. So in our case, we want to have a real-time inference service which serves our trained models. So let's imagine this application is training a model which can predict if a given flower, based on its characteristics, is the flower of genus Iris virginica. Now we can do this based on the open data set of Iris, and we can train a cool logistic regression model on this, and have all the orchestration of training and deploying and serving this abstracted away from us, so we can focus solely on developing our code. So after we define a service, we want to define endpoints so users can access your service. Usually we do that via HTTP protocol, a web call, and we navigate to some address within the server. So all the user needs to do is define the address they want, the path, and which function in which model of their code they want to invoke. And that's it. That's all they need to know about developing services in order to achieve that. The next section that we have in the YAML file describes pipelines. So pipelines, unlike services, are applications that aren't constantly running, but usually invoked on some schedule. So in our example, we want to have this model be trained on a schedule, let's say on a daily basis. If we have a lot of new data coming in that we want to train on, and so forth. So I want to define a pipeline of actions that will take place on a schedule and run my code, again, with the most minimal knowledge needed. So in our YAML file, we define a pipeline as a set of tasks which we want to have run sequentially on a schedule and depend one upon another. So if one task fails, you don't proceed to the next task. So they can achieve this by defining a pipeline, as you see here on the screen. They define here 2 tasks. The first task is running the training code. So this will invoke the code and the model and function that they ask to invoke. And in this case, they simply pass a Python command, so the most flexibility they can have. And this will train the model. The next task defined here is called validate. This will validate the model we just trained, and if it passes validation, we'll deploy it to production, where the serving service that we have constantly running will be automatically updated by that deployed model, and we'll be able to serve the newest model. That's the whole thing. That's what we want the users to do, have this minimal effort put in to achieve production-grade applications with monitoring and alerting and everything you expect from modern application. So let's look over the rest of the code. This will be non-liminal code, but user code in our example. So here I created a rudimentary model store using Amazon S3. We don't really need to get into the code here, but what I want you to take away is that we can upload models, save them, and we can download the latest model. So get the latest model that exists, and it's cached here and refreshes every so often. Obviously, this is not an optimal implementation, but just for the purposes of our demonstration, this is the model store that we have. And next, we have a requirements file. As in every Python project, they define the requirements and they add liminal, so they can have access to the liminal command line interface. Next, we have all the code that we require for them to write for serving. So again, we want minimal to no intrusion on user code. And as you can see, this whole thing is user code and does not import anything that any data scientist would already be working with. So what they do here is they call the model store to retrieve the latest model, and based on an input, return the output of the model. So most simple method ever, they receive an input in JSON and return a result as a string. And that's all that we require from them. And if you recall in the YAML file, this is the function that we were referencing in our endpoint in the service. So when people call predict endpoint on our service, it will run this function. So as simple as that, they don't need to know anything, just define a function, receives a JSON, returns a string response. And the next file, we have the training file. So here is pretty much boilerplate logistic regression model using the Iris dataset from scikit-learn. And the code here, in the training function, we train a model and deploy it, save it to a candidate model store so as to not affect production. In the next function we see here, validate, which is the one that we invoke in the second task in our pipeline. We validate that the model in the candidate, the latest candidate, is valid. So here, in this example, there's not many actual validations. We just check that the model can be read and can be used without crashing, but you can expect actual applications to have business validations of a model before deploying it. Once all validations have succeeded, we proceed to save the model to the production model store. And then next time that the serving application reaches a time to live on its cached model, it will check again for the latest model, and it will receive this new model that was trained. And that's how they talk to each other. Again, you see in the code, in the user code, there's nothing to involve liminal, nothing to involve anything other than boilerplate Python code that runs scikit-learn code. So let's see a demo of running this application and see what that looks like. So the user can interact with liminal, if not doing so through some CI pipeline, as we mentioned before, but stay on a local machine, through the liminal command line interface. So the first command we'll want to run is liminal build. Liminal build will create a Docker image or Docker images defined in the YAML file as user source code. So again, we don't want them to know anything about Docker. They just reference the location of the source within the repository, and we create a Docker image for them out of this. Then we have liminal deploy, which allows us to deploy our YAMLs to a liminal runtime. The current available one is using Apache Airflow, which is another project in the Apache organization that we believe in and work with. So once we deploy our YAML there, our pipelines are ready to run. And we can run liminal start to start the liminal server, in this case being Apache Airflow server. So let's see what the result of these commands looks like. So here's a pipeline running on Airflow, and it has the steps that match the tasks defined in the YAML that we saw. So again, with pretty much a click of a button and definition of the YAML, the user now has a deployed scheduled pipeline with monitoring running on Airflow in this case. But again, liminal is built to be extensible and built to be pluggable into different runtimes. So that's what the pipeline run would look like. What would the server look like? So let's have a look. So here's a request to the server that we started with. The image resulted from liminal build. As you can see, we send a request to the predict endpoint as defined in the YAML, pass it a JSON body, in this case, input about a flower, describing a petal width. And the response from the service that we get is the probability of that being an Iris virginica, which is what our model predicts. So in this case, 0.8 something, so 80 something %, that it is an Iris virginica in this case. Let's take a look at the logs of the server at this point. So as you can see here, a Flask server was started and a request was made which prompted our prints from our code to print to the screen, to the log, the input that was received, the model that it received from the model store, the cached model it received, and the result that it returned, which matches what we saw in the request. And that's it. That's all that we require from data scientists to have production-grade applications that are running and monitored and alerted in production and fitting the organization's existing stack with as minimal effort as can be from the organization. That is our goal. So what is next for the project? One of the things we intend to tackle first is CI integrations. So as we mentioned, we want Liminal to be able to run in different organizations and different stacks. And we want to supply CI code, which allows people to introduce Liminal into their existing stack without any intrusion, as we can. The next thing on the list here is user interface. While what we described up until now is very simple, we want it to be simpler. So we want data scientists to register these sorts of applications via user interface. So not even know that YAML and the YAML language required. That is another barrier we don't even want to have. So we want to have a friendly wizard that guides them through drop-downs where they define the application that they want, the code base that they want, possibly representing what data exists in the company, and the sky is the limit. We also want to integrate with existing ML frameworks that are being used today in the industry, so Kubeflow, MLflow, different feature stores, and so forth, to make that easy for users to engage with. Experiment tracking, to provide users with experiment tracking information. This can, of course, be related to the user interface path that we want to go to. Cloud support, we want to natively support all clouds to run Liminal on, so be it GCP or AWS or Azure. And we want to introduce a model store as part of the platform. So we want to, again, integrate with existing solutions, for example, MLflow's model store, and allow users access to that in a simple manner, again, via an application definition and no code required. At the center of this all is the open source community. So while we're dreaming big here, and there's a lot of things that we want to achieve, we cannot achieve them alone. We can achieve some of them, but what we want is together to achieve something great that we can all use. And we are great believers in Apache and the Apache way and the many eyes principle, and believe that if we can get contributors from different companies, different countries, then we can have different ideas, different contributions that can help make this project great. So what we would like is to invite you to join the effort. And you can join us on our website at liminalapache.org and join our mailing lists. You can see the project on GitHub and see the issues tracked in Apache's Jira and try to tackle them yourself. We are looking for contributions. We have, again, want to lower barriers on contribution as well and be able to accept contributions from you in the smoothest way possible. So together, we believe we can make great things happen, but we need your help. So come join the effort. We are open on the mailing lists. Talk to us.